Now, let's bring it back to thermodynamics. We've seen that positive values of E, our cell potential, or electromotive force, whatever you want to call it, is when it's positive, those are spontaneous reactions. We also know that when delta G is negative, we have spontaneous reactions. And indeed, there is a relationship between them, so that we can calculate the delta G value for any redox reaction that we can measure its cell potential. And the relationship between them is the following. This is called the Nernst equation, where we are relating delta G to our cell potential. And we can put the standard conditions on here if we were so inclined. We don't necessarily need standard conditions, but we have them. So this is where, by the way, the moles of electrons come in. Since we haven't had to worry about that with E, right? We don't multiply E by anything. We just add them together, or subtract them rather. Your reduction minus your oxidation. Don't forget that. So remember that E for your cell or process doesn't have to be in a cell, in an electrolytic cell, but we might say it is. So let's just say E for the reaction is the reduction one minus the oxidation one for your overall reaction. So with this, we're going to see that that's what E stands for. F is Faraday's constant, which I have written down here, which is 96,485 coulombs per mole or joules per mole, that we typically will see it in, whichever unit you like. That's an important constant we're going to use. And then N is the number of moles of electrons in the reaction. So remember when we were balancing those half reactions and putting them together and we had to make them have the same number of moles of electrons? We need to remember that number N here for when we're calculating delta G. So we can do that, for example, for our last problem. We looked at this copper and zinc fun stuff. We saw that this is a 2-electron process. Both our half reactions had 2 electrons. And our cell potential was 1.097. So for this, we can go ahead and find delta G. Delta G for that reaction was negative 2 times 96,485 joules per mole times 1.097 what's its we can put this in coulombs per mole. Actually, it's joules per coulomb, right? Because a volt is a joules per coulomb. So we can put it in either way, the Faraday constant. So we'll put it in coulombs this way because the coulombs will cancel out. We don't really need to worry about units. Delta G is always joules per mole or kilojoules per mole, depending on whatever we need it to be. So we'll have that out there. Plug it into the calculator. Delta G for this process is negative 2 times 96,485 times 1.097. We get negative 211.7 kilojoules per mole. So very it's called exergonic technically, a very spontaneous reaction, we can say. And we know that because we had a positive value of our electric potential. So that's actually a pretty big delta G, magnitude-wise. So this is a nice spontaneous reaction. It's going to work very well for us. How can we double check? Simple. Go to the back of your book or appendix D or whatever. Find the delta G values for copper plus 2+ and zinc 2+. See what they are. Do products minus reactants, and see what you get. You should end up with this number or something very similar to it. So we can calculate delta G for a reaction. That's all well and good. But what's the purpose of delta G again? What was the whole point of doing that thermodynamics chapter? Well, we should probably remember that delta G is RT ln K with a negative sign. Yes, negative RT ln K. Remember, we can calculate our equilibrium constant by knowing the delta G. So we can calculate the equilibrium constant for this reaction as well. Hooray! All of our favorites here. And of course, we can relate if we plug in this delta G substituted into our Nernst equation here. We can get negative NFE is equal to negative RT ln K by plugging in delta G. If we solve, we can solve first for E. Our cell potential would be RT ln K over N times F. Hooray, we can do that. Alternatively, if we were so inclined, we could also solve this for the equilibrium constant. Ln K, if we solve that, would be NFE over RT. And so if we were to do the anti-natural log, which is e to the, that means K is equal to e to the NFE over RT. And so we can have it done this way. So, very useful stuff. We can now go from cell potential to equilibrium constant. Let's calculate the equilibrium constant for this reaction here. If we wanted to do that, we can say K for the same reaction is e to the 2 electron moles times 96,485, that's Faraday's constant, times our cell potential 1.097, divided by R will be our gas constant 8.314, times our temperature, which is 298, since we haven't looked at other temperatures yet. Make sure you use a lot of parentheses on this because we have a lot going on in the exponent. Alternatively, do all this multiplication, division, and then do e to your answer. That's how I'm going to be doing it. So 2 times 96485 times 1.097. Divide this number by 8.314. Divide this number by 298. I have 85. That's huge. E to this answer becomes K is equal to 1.28 times 10 to the 37th power. Isn't that incredible? Extremely spontaneous reaction. So we may not see it as very important when we look at that cell potential 1 volt. Wow, so amazing. It really is. Look at how spontaneous this reaction is. This reaction overwhelmingly favors the products and will move very rapidly. Those electrons move at the speed of light towards making this happen. So we can figure out the equilibrium constant of our reaction, knowing the cell potential. So fun stuff we can do with this. All right, so that's it for this week. We'll leave it here. Next week, we'll take a look at incorporating non-standard potentials, meaning things that's not at 1 molar and 1 atmosphere of everything, or maybe a different temperature. So we can mess with all that next week. So happy studying, everyone, and we'll see you next time.